to understand the concept of space filling, we have certain models here which will explain us. First, we shall start with 2 dimensions, then we shall go to 3 dimensions in order that we understand the concept of space filling. So let us look at this cut pieces of paper which I got here, which we shall illustrate to understand the concept of space filling. Here I have with me a pile of square cardboards, a pile of triangular ones, pile of hexagonal ones, and a pile of pentagonal ones. In addition, we also have certain rhombus shaped cardboards. Now we know that these shapes, the triangle, the square, the hexagon and the pentagon, form the series which is a part of the infinite series of 2-dimensional figures which are called the regular polygons. Now let me start by illustrating the concept of space filling in 2 dimensions by using these square cardboards. So I take a single cardboard and then I put another cardboard, then I can put a third cardboard, then I can go into the second dimension. This was along the first dimension. Then I can go into the second dimension and put more of these cardboards. Assuming that these additional cardboards are also of the same color, I can go on and put more of these cardboards, and I can repeat this pattern infinitely in 2 dimensions. So I have a repeating pattern which is infinite, say along the x direction and also along the y direction. Of course, an important property of such a space filling is that I can actually translate a row with respect to the remaining rows, assuming that these rows are infinite, to continue to have a space filling tessellation. Tessellation I means that this tile, which is now a single tile, can go on to fill space in 2 dimensions. Now I could do this in a little more complicated way as well by taking a sheet of paper and then shifting various rows with respect to the other rows, and still I can achieve complete space filling in 2 dimensions. So we see that square can, as a single shape, which we use the term monohedrally, square can monohedrally fill space, and that too in infinite number of ways. Of course, if I constrain that one vertex of the square has to match with another vertex, then of course I have just a single pattern, which is what we started off with. Now let us proceed to the triangle and the hexagon to see how they can fill space. And now we are talking about 2-dimensional space. So I take a triangle, I put one of them, then I can put another triangle, and I can put another triangle, I can put another triangle, and I can put another triangle, and then assuming that this triangle is also of the same color, I can put another triangle to actually obtain a hexagon. And now since I have obtained a hexagon, I will proceed to actually show that hexagon can fill space, and if hexagon can fill space, then obviously triangle, which is 1/6 of an hexagon, can also fill space, and of course again 2-dimensional space. So let me move this pattern to the top, which I have created here. Then let me put these hexagons. And if I assume that these hexagons are also of the same color, then I can go ahead and put more of these hexagons, which can actually fill the 2-dimensional space. This is nothing but the familiar honeycomb structure, which all of you might have seen before. So I can repeat this pattern in 2 dimensions, but in this case I have no flexibility to actually translate one row with respect to the other. In other words, if this row sits here, I cannot move this row and continue to fill space. As you can see, if I try to do that, then there will be gaps which will develop in the space which I am trying to fill. So I have clearly seen that squares can fill space, triangles which are 1/6 of this hexagon can fill space, and hexagons themselves can also fill space in 2 dimensions. So let me try the same procedure or the same exercise by considering these pentagons, and we will show that actually pentagons cannot fill space, and that's a very important point. And when I mean pentagons cannot fill space, I mean the regular pentagon. The regular pentagon cannot fill space. So let me try anyhow how these pentagons can start, or at least how can they be put onto a 2-dimensional surface. And as before, I will assume that these pentagons are also of the same color. And I can go ahead and do this process infinitely. In doing so, I clearly observe that there are actual gaps which develop in the filling of space. Therefore, we see that pentagons cannot fill space, but the gap which is left is actually of a particular shape. It happens to be a rhombus shaped gap which is opening up. And now suppose I had rhombi which are like this, and I put them into this little space, then I can actually achieve a space filling now which is not made of one single type of tile, but actually made up of two type of tiles, a pentagonal tile, a regular pentagon, and a rhombus. And as you know, a rhombus is not a regular geometrical solid, because even though its four sides are identical, its included angles are not the same. That means one vertex is different from the other vertex, and therefore this is not a regular n-gon or a regular polygon. So by putting two of these together, I can actually fill space, and this is called dihedral tessellation of space. That means I have two shapes, that's why the word dihedral, and therefore I have a dihedral tessellation of this two-dimensional space. And we had seen before that squares, triangles, and hexagons can monohedrally fill space. Now we can ask ourselves the question, suppose I relax the requirement that I don't want to use a single shape, how many different possibilities exist, and one of those possibilities we have seen now. Or I relax the requirement in a different way, that I don't use regular shapes, then how can I fill space? This is a much larger problem, but one interesting fact I would like to point out now, that if you don't use regular pentagons and a certain kind of a pentagon which is non-regular, then you can actually fill space with pentagons monohedrally. So remember, it is not a regular pentagon which is going to fill space, it's a non-regular pentagon which can fill space, but importantly monohedrally it can fill space. And an example of this has been found in Egypt. That means prehistorically or historically people have known how to use pentagons to fill space, again the non-regular pentagon. And the question that how many such pentagons exist, the non-regular ones which can fill space, is an open mathematical problem. So briefly we have seen here that the concept of tiling, that means how you can use a tile to fill space in two dimensions. We have also seen that only certain kind of tiles can fill space without leaving gaps, and those examples we have seen here. And one important point we saw, that pentagons cannot monohedrally tile space.
So I have one question.
There is a question from Mr. Patel.
If we suppose there is some pentagon, we want to make a crystal, so we cannot obtain perfect crystal, only pentagons.
Mr. Patel's question is that suppose I want to make a crystal out of pentagons, can I have a crystal which has got these pentagons as their motif? A very, very important and very profound question. There are two issues here. One is the issue of symmetry, and the other is the issue of actually filling space with a certain kind of an tile. The issue of symmetry is that actually not related to the concept of space filling. To give an example, tetrahedra cannot fill space, but we do find tetrahedral symmetry in crystals. In fact, tetrahedral symmetry belongs to the class of cubic crystals. If you have a crystal with tetrahedral symmetry, that would be one of the cubic crystals. But so therefore we have to decouple the issue of an existence of space filling structure with the existence of symmetry in a crystal. So these two are different issues. Coming to the specific question of pentagons, yes, pentagons cannot fill space, and there are no crystals which have pentagonal symmetry. And it's worthwhile to add at this point of time that there are other structures which have pentagonal symmetry, and these are called quasi-crystals, and especially there is a particular kind of quasi-crystal known as the icosahedral face, which has something known as the icosahedral symmetry. And if you look at an icosahedron along the five-fold direction, you will actually see a pentagonal symmetry. Therefore, you can perform an experiment like a convergent beam electron diffraction pattern from a pentagonal icosahedral crystal along the five-fold direction, and you would see such a kind of a symmetry. Therefore, to re-emphasize the point, space filling and existence of symmetry in crystals are two different questions, and pentagonal symmetry does not exist in normal crystals, but they can exist in certain kind of quasi-crystals which are for instance the pentagonal quasicrystals or the icosahedral quasicrystals. To understand the concept of space filling, I have here with me some models on the table here, and to help me out with this concept I will request Mr. Arun Kumar, a research scholar in our department, to help me out with holding these models and also in the explanation of the concept of space filling. Okay. So let me start with the case of the cube. We should know that a cube, for instance, this is a cube which is sitting on the table right here, is a space filling solid. And this is perhaps the simplest example which we need to consider when we want to understand space filling. So I have got smaller pieces of the cube to illustrate the concept right here, like this is a small piece of a cube which is there for us to understand the concept of space filling. In addition to these examples of the cube, I have also got something this shape of a solid which is known as the tetrachydecahedron. So I have got a cube, I have got a tetrachydecahedron, and in addition I have got something known as the rhombic dodecahedron. But before we go on to these more difficult examples of the tetrachydecahedron and the rhombic dodecahedron, let us consider the example of the cube. So what is that we want to understand is that the cube is a space filling solid. So let us take a cube and I can put together these cubes in a row. So let me put them in a row. And I can go infinite in one direction. To simplify matters, I have got a larger block here which is equivalent to this row of cubes. So I can take one row of cubes, I can put a second row of cubes, I can put a third row of cubes, and so forth in the second direction. The first direction was made up of the smaller cubes arranged in a row. The second direction was these rows themselves arranged in the other direction. Suppose this were my A direction, this would be my B direction. Now, to understand this set, I have an alternate piece here which is nothing but a combination of these kind of rows put together in the form of a block. So let me consider this block now. So I have a block here which is a combination of many of these single rows like this put together in a form of a block. Now, because now this is three-dimensional space, the third direction I can stack these kind of blocks to create a larger block. And so forth. Now suppose this row which I created in one dimension originally was infinite in this direction. In other words, instead of considering a finite block like this, I had an infinite block, then each one of these two-dimensional blocks would also be infinite, and in 3 dimensions I would get a solid which is space filling in 3 dimensions. An important point to note when we are dealing with this kind of space filling with these cubes is that I could have actually taken a row like this, for instance, and put the next rows at some distance or some sliding with respect to the first row, and even an arbitrary sliding of the second row and some other arbitrary sliding of the third row and so forth. And since these are infinite rows of cubes, such a block would also be space filling. In other words, if I were to look at these individual blocks, what I am trying to do is that I am putting these blocks in any kind of an order. There is no perfect order, but still these shifted rows would also perfectly constitute a space filling pattern. So you can see here I can construct a space filling pattern, and of course I can grow this in 3 dimensions by putting some more blocks at random positions. So I can start with a row of cubes, create a space filling row, then create a space filling block like this, then I can create a space filling 3-dimensional space of layers by putting many of these blocks together. And as I suggested before, I could actually translate these blocks and create a random stacking of these blocks, and since each one of these blocks is infinite, I would get an infinite three-dimensional pattern which would completely fill space. Now, in the examples we are about to consider later, we would see that this kind of a freedom is only available in the case of the cubic block and not in the case of some of the other examples we are going to consider. This is because the cube has very high symmetry and it can fill space in this many different ways. And when I look at a single cube, for instance this cube, we already clearly notice that cube is nothing but a platonic solid. It is a regular solid, and therefore every edge of the solid is identical to every other edge of the solid. Every vertex of the solid is exactly identical to every other vertex. So it does not matter if I pick this vertex or this vertex or this vertex, it's identical. Every face of the solid is exactly equal to every other face in the solid, which is nothing but a square. So this is a highly symmetrical solid, and therefore it is called a platonic solids, and there are 4 more platonic solids apart from the cube. But this is the one which has got the property of space filling, and none of the other platonic solids can act like space filling solids. The second convex polyhedra, or the geometrical shape I have got here to explain the concept of space filling, is the solid known as the tetrachydecahedra. The tetrachydecahedra can be obtained from an octahedron by cutting off the vertices. That means suppose I extend these edges along, I would actually get an octahedra. I shall have to extend all the vertices to get an octahedra. By cutting off those vertices of the octahedra, I can obtain this kind of a solid which is known as a tetrachydecahedra. The cutting procedure has to be done in a way so that the length of this edge is equal to the length of the other edge. This is clearly not a regular solid, because you can see that there are 2 kinds of faces that this solid has got. It has got a red face which is a square, and it has got this transparent face which is hexagonal. So clearly this is a solid of lower symmetry having 2 kinds of faces, a square face and an hexagonal face. Let us look at the edges. It turns out that the edges of the solid are all identical, because every edge exists between a square face and a hexagonal face. Let us look at the edges of this solid, and we see that edges are also of 2 types. One edge exists between the square face and the hexagonal face, and the other kind of edge is between one hexagon and the other hexagon. So while the cube had only one kind of an edge which was between 2 square faces, here there are 2 kinds of edges, one between the square and the hexagon and one between the hexagon and the other hexagon. Now let us look at the vertices. The vertices, for instance this vertex, is there between one hexagon, another hexagon and a square. Let us look at another vertex. So this is between one hexagon, another hexagon and the square. Look at the third vertex. So this is between one hexagon, other hexagon and the square. In other words, in some sense, all the vertices are identical in this solid, which is a tetrachydecahedron. Now let us try to understand that this solid, which we pointed out was a special kind of a truncation of the octahedron, has a very important property, which is the space filling property. So we had already seen that there is only one platonic solid, which is the cube, which has got a space filling property. This is a semi-regular solid of lower symmetry, which also has this space filling property. So Mr. Arun Kumar will help me with the arrangement of these tetrachydecahedra to obtain a space filling solid. So you can see that he has put in one tetrachydecahedron with another tetrachydecahedron, so that the common interface is actually the hexagon. Now you will have to take the third tetrachydecahedron and place it in a way such that these 3 together touch each other. You hold the 2, I will hold this one. So you see that those 3 have actually touched each other. So let me rotate this a little bit to show you that actually it has got this property that it is touching along the hexagons. So the hexagon of this tetrachydecahedron is touching the hexagon of this tetrachydecahedron, the hexagon of this tetrachydecahedron is touching the hexagon of this tetrachydecahedron, while the square face of this tetrachydecahedron is touching the square face of this tetrachydecahedron. To show actually this is space filling, let me put one more in the third dimension. So I'll put this in such a way that this red face of mine matches with the red face of that, and you can see that you actually obtain a three-dimensional structure. Of course, this is only part of the space filling structure. So there are these 4 tetrachedecahedra, and you could, if you join the centers of this, you will actually obtain a tetrahedron, and I can actually allow this structure to grow in 3 dimensions, so that this now becomes a space filling solid. I have only shown a part of this tessellation, but in effect this has to be done infinitely in 3 dimensions to actually obtain a structure which is this space filling solid. So just to review, let me do this whole process again, wherein I take 2 tetrachedecahedra, match the hexagonal faces of these tetrahedra, and it has been matched now, and after matching it I will take the square face of one tetrachedra and put it on the square face of the other tetrachedecahedra to obtain a structure which consists of 3 tetrachedecahedra, and then after that I will match the red face of this, which is a square face, on to this to obtain a tetrahedral configuration of these 4 tetrachedecahedra. So after this we will have to do this process ad infinitum by matching these tetrachedra in 3 dimensions to actually obtain complete space filling. An important point to note when we are considering such a shape is that many people actually use this shape to model grains in crystals or in materials. They actually use this as the shape of the grain. In other words, this itself will be considered as a single crystal, and grains would be modeled based on this shape, because this has got the property of space filling. In other words, when I want to make a model of a microstructure wherein this performs the role of a grain, then all I need to use is one solid, which is this solid, which will be the model of a grain. The third solid which I want to use to illustrate the concept of space filling is the solid known as the rhombic dodecahedron. In this rhombic dodecahedron sample I have got in my hand, I have colored some of the faces in different colors, but you should remember that all the faces are actually rhombus. And how many of these rhombic faces has it got? When you count this, it will actually turn out to be 12, and that is why the name dodecahedron, because it has got 12 faces, as compared to the solid which we had considered before, which had 2 types of faces. This has only 1 type of a face. Nevertheless, this is not a regular polyhedron, and the reason it is not a regular polyhedron is that the face itself is not a regular n-gun. If it were a square, then I would have a cube, which would be a regular polyhedron in 3 dimensions, or it has to be one of the regular n-guns like a triangle or an octagon or a regular pentagon. But since rhombus is not one of those, this itself is actually a semi-regular solid and not a regular solid. Now let us look at the edges of this solid. The edges are all identical because they are between 2 rhombus. So you can see this is an edge between 2 rhombuses, and this is the edge between these 2 rhombi. If I look at the vertices of this solid, you will notice that there are 2 kinds of vertices. One which has 4 rhombus or rhombi sitting around it, and those vertices which has only 3 sitting around it. So this semi-regular solid has only one kind of a face, it has got only one kind of an edge, but it has 2 kind of vertices. The 2 kind of vertices are those having 4 of these rhombus around it and those having only 3 around it. So let us consider how we go from a single rhombic dodecahedron to actually a space filling rhombic dodecahedron. One point to be noted while we consider this rhombic dodecahedron, with suppose by placing this 2 vertices which are 4 of them top and bottom, is that this has been called the least photogenic solid. In other words, actually unless you have a model in front of you, it is very difficult to either draw this or try to understand this solid from a video recording like this. So I would strongly urge you all to actually make a model of this 3-dimensional solid and try out this space filling experiment, because it's actually very difficult to visualize this kind of a solid merely from a 2-dimensional projection. So let us go ahead and create a 3-dimensional space filling model, and Mr. Arun, our research scholar, will help me in this process. So he has put 2 of these with 2 rhombus touching each other, and I go ahead and put a third one into this process. Can you just hold it so that so which face goes down here, right? So now what I have done is that I have taken 2 of this rhombus which had rhombus faces sitting touching each other, and then I put a third rhombus, and I can see that there is this space created. So these are this vertex which is common to these three dodecahedron, rhombic dodecahedron. There is one more vertex at the bottom which is also common to these three. Therefore, there is one edge which has been shared between these three rhombic dodecahedron. Clearly, since you can see that the vertex which I need to put on top of this rhombic dodecahedron has to be a 3 connected vertex and not a 4 connected vertex to make this a space filling solid. Let me take, for instance, this 3 connected vertex and put it on this to actually create a tetrahedron of these rhombic dodecahedra, which is a space filling structure. Of course, to actually see it to be a space filling structure, I will have to put an infinite number of them in 3 dimensions, but it is clear from this model that it can perform the role of a space filling solid. So, to understand space filling concept, today we have taken 3 geometrical convex polyhedra, the first one being a cube, the second one being a tetrachedron, and the third one being a rhombic dodecahedron. The cube is all familiar to us, and it can fill space in an infinite number of ways if we do not impose a condition that a vertex of one cube has to match the vertex of the other cube, or in other words, an edge of a cube has to match the edge of another cube. But these two solids can fill space in only one way, and that way is pretty much unique. In other words, the matching rules we have seen while we actually did the construction, and we had also seen that this is a regular convex polyhedron, the platonic solid, while these two are semi-regular, and they are semi-regular in different ways, that there are 2 kinds of faces for this kind of a solid, while here there is only one kind of a face, but there are 2 kinds of vertices. Here there are 2 kinds of edges as well, the one which connects hexagons and the one which connects a square to a hexagon. Let us explore the concept of tessellation. Tessellation means putting together tiles, which could of course be 1-dimensional, 2-dimensional, 3-dimensional tiles, to fill or put them in various dimensions of space. Now, tessellations can be of 2 types. Space filling and covering. In space filling type of, there is no overlap allowed, but there are gaps in space allowed. To give an example, I have a model here. This is a space filling model in which spheres have been used to do a space filling tessellation. In this space filling problem, obviously you can see that there is no overlap between the balls which are here, which are nothing but table tennis balls, but there are gaps left which are nothing but the seats of the void. On the other hand, suppose I am talking about covering. Here we are allowed no gaps, but we are allowed to do overlaps. To give an example, let me consider these pentagons and let me show them to you. Suppose I want to put these pentagons together, then I can actually put them in a way such that there is an overlap of one pentagon, and you can put all of these together to actually cover the space completely, but you can see that there is overlap which is allowed. So let me show you in this view that these pentagons have been put together, and I can keep putting these pentagons so that there is an overlap. Of course, this is a very random way of putting them together. You can use more regular ways of allowing this overlap, but you can put these pentagons to actually fill space. But in this case, you can clearly see that the 2-dimensional space, there is no gaps left, but there is definitely an overlap between the tiles. In this case, it happens to be a pentagonal tile I am using to actually cover space. Of course, we have to be very clear, this is a 2-dimensional example and this is a 3-dimensional example, and of course I could also construct a 3-dimensional examples of covering wherein you allow overlaps but you do not allow any kind of gaps. Okay. We will briefly revise the question that why some of the possible 2D lattices are missing, but now with a little focus on the symmetries of the lattices. So if you look at the doubly non-primitive cell or the primitive cell, you can clearly see that it has got a symmetry layout which is exactly 4 mm. Therefore, the primitive and the non-primitive, both the cells have a 4 mm symmetry, and therefore I would rather go in for the smaller primitive unit cell. We also said that the centered rhombus lattice is nothing but the simple rectangle lattice, and that's also clear looking at the symmetry layout on the rectangle lattice, and you can see that the symmetry layout is exactly identical to the simple rectangle lattice which we had considered before, and it does not have the hexagonal symmetry, which is what a rhombus lattice should be having. Therefore, either based on the concept of the choice of the unit cell or based on symmetry, things are coincident here. For the other case, which was the case of the centered parallelogram lattice, we chose the simple parallelogram lattice, and we see that the symmetry overlay on the parallelogram lattice is exactly identical to that of the normal parallelogram lattice, and therefore I would use a rather smaller cell, which is the alternate smaller cell, which has the identical symmetry to that of the parallelogram lattice which we had considered before. I would like to show you that the choice of unit cell is something which can lead to considerable confusion, especially when you try to contrast it with the concept of a crystal. So for instance, suppose I ask myself this question: if the definition of a crystal is based on the symmetry, and for peeking a little ahead, and we know that there are 7 crystal systems and these crystal systems are based on symmetry, then how come we have statements like, which if you look at any standard textbook you will find a statement like this, that A equal to B equal to C, alpha beta equal to gamma equal to 90 degrees is a cubic crystal. So we are asking the question, crystals are based on symmetry. For instance, cubic crystal would have a certain kind of symmetry which we will consider very soon, and lattices on the other hand can be described by these kind of unit cells, and we have seen there are unit cells which are also in the shape of a cube. And this point is a point of considerable confusion, and we will take it up in a lot of detail very soon, but even at this point of time it requires some amount of clarification. The important thing is that though the definition of crystals, for example a cubic crystal, is based on symmetry and not the geometry of the unit cell, please note again the word not is very important, it is not based on the geometry of the unit cell. It is true, it is however true that if you already have a cubic crystal, that means somebody gives you a cubic crystal and asks you to choose the most logical unit cell or the most logical choice of the basis vector set, then you would go in for a cubic kind of a lattice parameters, which is A equal to B equal to C and alpha beta gamma is equal to 90 degrees. So in this case, if you already have a cubic crystal and you want to use the most preferred set, and as I said, the word is preferred or logical and not the only possibility. We have seen that actually the choice of unit cell is completely left to us, but then there is always a preferred or logical set, and the very next slide will tell you that how a preferred or logical set is actually logical. So that also will become clear from the next slide, which will give you an example by citing the example of a crystal circle. So let us consider a circle, and now I will use 3 kinds of axis systems, 2 of them being the orthogonal normal Cartesian coordinate systems, and one will be a polar coordinate system to describe a circle, a simple circle described by a 2 Cartesian coordinate system, the one here on the left and the one below that, and one polar coordinate system. Now equation of a circle, suppose I want to describe the circle in terms of this left hand or the Cartesian system given on the left hand side of the slide is x minus a the whole square plus y minus b the whole square is equal to r square, right? Now let me now move the circle to the origin, which is the 0, 0 point in the Cartesian coordinate system, okay? And if I do that, I get the figure which is below. Now it is obvious that the circle has not changed in any way. The symmetries of the circle remain completely the same as before. So for instance, what is the symmetry of the circle? Any kind of rotation would leave the circle invariant. In other words, it's got an infinite fold axis right at the center. Obviously there are mirrors. You can draw any kind of mirror passing through the center, and that will be a symmetry of the circle. You could pass the mirror, for instance, at this angle or horizontally or any angle if you wish, and the circle will maintain its symmetry. Now by just merely changing the coordinate axis, I have not altered the symmetry of the circle. It's obvious. But let's look at the equation describing this circle. what is the equation? The equation is x square plus y square is equal to r square. And as you can clearly see, this equation is simpler than the equation which was written above, wherein the center of the circle was at AB and not at 0, 0. So, by merely choosing an appropriate origin for this rectangular or a Cartesian coordinate system, I can actually make the equation simpler. Now, let us see if any further simplification is possible, and it is possible because now I can use a coordinate system which is exactly the kind of symmetry which a circle has got, and we have one of these, and this is known as the polar coordinate system. And on the right hand side, if I try to describe the same circle in terms of the polar coordinate, which is rho and theta, then I get an equation of circle where rho is equal to r. In other words, the radius is a constant, which is what is reflected in this equation, rho is equal to r. Now, to emphasize the point once again, the circle is described equally well by the three equations, but it is clear that the polar coordinate system with the center of the circle coinciding with the origin, again in the polar system, again I am making sure that my center of symmetry of the circle coincides with the origin of the polar coordinate system, which is obviously the logical choice. The equation takes the most simple or the most elegant form. So, from this example, it is very clear that I can choose any kind of a coordinate axis or any kind of a coordinate system to describe the circle, but there is a preferred one, and the preferred one is dependent on the symmetry of the structure I am trying to describe. The structure I was trying to describe in this example is a circle. Therefore, for the circle, the most preferred choice was the polar coordinate system. By the same analogy and by the same token, when I am trying to describe crystals, there is a logical or a preferred choice of coordinate axes, but by no means should I confuse that choice of coordinate axes with the actual object I am trying to describe, or actually the symmetry of the object I am trying to describe. We have clearly seen in this example that the circle does not change its symmetry in any of the way I consider it or I describe it by a coordinate axis. The symmetry of the circle remains exactly the same, but my description is more convenient, it is more logical, it is more simple if I use a kind of a coordinate axis which matches with the symmetry of the object I am trying to choose, or at least some aspects of the symmetry of the object if there are any of them present. So, our choice of coordinate axis does not alter the symmetry of the object or of the lattice. So, if the symmetry of the object I am talking about here is a crystal, then my mere choice of the coordinate axis is not going to change the crystal in any way, and that we will see, of course, in considerable detail very soon. Before I take up some examples of three-dimensional lattices and also take up examples of crystals made out of these one-dimensional, two-dimensional and three-dimensional lattices, I would like to explore a concept known as the concept of a sub-lattice. Now, in some courses this would be left as an advanced treatment which would come later, but this being a simple and intuitive concept, and we have already described some crystals which can be very nicely described by this concept of a sub-lattice, I am considering it now. So, let us take a crystal. This is our familiar crystal which we constructed before, wherein we had a one-dimensional lattice which was decorated with a motif which had two entities in it, one up arrow and a one down arrow. In this example, the up arrow is green in color and the down arrow is yellow in color. And we had noted before that for such a crystal, the lattice points are the brown circles or equivalently the blue circles, but not both of them. It has to be only one of the two. Now, let us try to describe this crystal in the language of sub-lattices, and to do so I will split up this crystal into two halves, and both of them obviously are infinite because the crystal itself was infinite. So, I have a sub-crystal 1 which is made up of only green arrows, and I have a sub-crystal 2 which is made up of only yellow arrows. So, a sub-crystal 1 is itself can be described as up arrow sitting on these brown points, which is itself a lattice. Now, in other words, what I am saying is that the crystal X, which was the original crystal, can be thought of as a superposition of a subcrystal 1 and a subcrystal 2, and obviously the origin of the subcrystal 2 is shifted with respect to the origin of the subcrystal 1. Now, this so far we have been talking about subcrystals. So let us now talk about the sub-lattices which go on to make this subcrystals and itself the crystal itself. Now, suppose I consider this array of points over which these arrows, up and down arrows, were sitting. This itself can be considered as a lattice. Once I decorate this lattice with up and down arrows, I clearly see that the blue dot or the set of blue points no longer remains a lattice point. But if I just consider the array in independence, then I can always think of this as a lattice. I can now break up this lattice into two parts: the brown lattice, which is the sub-lattice 1, and the blue lattice, which is the sub-lattice 2. In other words, this lattice which I have constructed at the top can be considered as a superposition of two sub-lattices, the sub-lattice 1 consisting entirely of brown points and the sub-lattice 2 which consists entirely of blue points. Of course, you can clearly see that the origin of the brown lattice is shifted with respect to the origin of the blue lattice by this distance, which is half the lattice parameter of the original crystal. So, if the lattice parameter of the original crystal is A, then the lattice parameter of the sub-lattice or the shift in the two sub-lattices is A by 2. Now, so that is what is shown here. The original lattice parameter is given by the vector A, then the shift of the one sub-lattice with respect to the other sub-lattice is A by 2. Now, if I call this lattice, two lattices, as sub-lattices, then I would call the original lattice as a super lattice. It is called a super lattice not because it has got some super property like superconductivity or super plasticity. It merely implies in this case that the super lattice consists of two sub-lattices, and these two sub-lattices have been decorated with certain kind of entities, in this case up arrows and down arrows, to create a supercrystal, if you wish to call the crystal X, which is a superposition of these two subcrystals. Now, let us consider a two-dimensional example to illustrate the same point, which is the concept of sub-lattices and subcrystals. So, we have another familiar example which we had considered before, and in this case we have a two-dimensional crystal which has been created by decorating a two-dimensional lattice with a motif which consists of a green circle and a brown or maroon circle. And we had seen that such a lattice, suppose it were rectangular, would have two basis vectors A and B, and in the example we considered, A and B were inclined at an angle of 90 degrees. So, let us see how we can describe such a crystal in terms of the language of subcrystals and sub-lattices. So, if I call this crystal as X as shown here, and we have also marked on this figure the blue outline or the blue filled region, which is the unit cell of this crystal. Now, let us try to understand this crystal in terms of the language of sub-lattices and subcrystals. So, I am overlaying a grid on top of it, noting that the lines which form the grid have no physical meaning. It is only the vertices of these squares which have physical meaning, which are either lattice points or exactly between two lattice points in the crystal. So, now I have overlaid this grid. Now, I have got a green grid and I also have got a brown square grid which has been overlaid on this structure. Then I actually split out this supercrystal, if you wish to call that, into two subcrystals, the subcrystal 1 and the subcrystal 2, and you can clearly see the subcrystal 1 is fully decorated with a single circle motif, and this subcrystal 1 can itself be thought of as an independent crystal, wherein you got a square lattice, or in this particular example a rectangle lattice decorated with a green circle. Similarly, there is no difference overall between this this green crystal and the brown crystal, except that the brown crystal is now consists of a similar kind of an unit cell, but now decorated, this brown lattice has been decorated with a brown circle. So my crystal, which I can now call a supercrystal if you wish, can be thought of as a superposition of a subcrystal 1 and a subcrystal 2.
Excuse me, here both motifs are same or different?
Mr. Patel has a question that are these two motifs same or different? They actually happen to be different because I have distinguished the motif in terms of the color. Now suppose I go back to this crystal and I consider that the browns and were also greens, then you can clearly see that such a crystal would be a centered rectangular crystal and not a simple rectangle crystal, which is what you can see here. So this crystal you see here is nothing but a simple rectangle crystal, because what have you taken? You have taken an original simple rectangle lattice and you have put this motif, and we already saw a graphic video of how we put such kind of a two circle motif at every lattice point to actually construct this crystal. We saw the video of that. So then we go ahead and after making this simple rectangle lattice, we decorate each lattice point with this two circle motif. If suppose I make a consideration the way you have nicely pointed out, that if the brown spheres circles were transformed into green circles, then what would I do? I would take a centered rectangle lattice, again of course described by the basis vectors A and B, and I would decorate that centered rectangle lattice with a single circle which is of green color. So that would be a different kind of a lattice, and the crystal I would be generating in that case would be a centered rectangle crystal and not a simple rectangle crystal.
Actually, I have one question. If I make one Li, magnesium and aluminum like that, and in that case, both we have two types of motif. So we can describe that Li on the basis of subcrystals.
Very important and very valid question. So Mr. Patel has a question that instead of now these kind of spheres, I go into real systems wherein I have actual atoms or ions, as you might like. In this case, in the example cited by him or in the question by him, they consist of magnesium and aluminium ions or atoms. What would happen in this case? A very important question. Now we will actually return to this question in detail later, and we will actually consider practical examples. But suppose now I don't call them magnesium and aluminium, I call them A and B. Now it could so happen, typically it does happen that way, that many of these systems show a disordered alloy at high temperature, okay, wherein you would have a simple kind of a structure describing. In other words, the central lattice position would be decorated by something which is exactly identical to the one at the corner. But at low temperatures, if the structure gets ordered, which is what you can see here, this is an ordered structure wherein the brown spheres or brown circles occupy a particular sublattice preferentially compared to the other one. In such a case, I will have to describe it in the language which I am doing now in terms of a superlattice and a sublattice, or a supercrystal and a subcrystal if you like. So the ordered structure will be described differently compared to the disordered structure. So in coming lectures, we will take up those examples and nicely try to understand how those ordered disordered transformations and also their description in the language of crystallography can be done. And we will take up actually practical examples where this is actually found.
Excuse me, sir. Can we have more than two sublattices in a superlattice?
Oh, very good question. So Mr. Ravi Prakash Srivastava, our research scholar, has a very important question. He is asking that can we have more than two sublattices? Definitely we can have more than two sublattices, but then those sublattices have to be occupied by different kind of species. Okay. Or there has to be a description of one of the sublattices which has to be different from the other sublattices. In other words, there is no point for me to construct a sublattice, for instance in this figure, at an origin at quarter here, right somewhere between the two, and leave it empty. There is no point doing it unless I have some species or something to decorate that point. So if I have something to decorate that point which is different from the decoration of the other two sublattices, then there is a meaning for me to define those sublattices, and it is done if you have a ternary ordered alloy. For instance, going to a more practical example, then you would use three sublattices and you would put certain preferential species on those sublattices. Further, just to peek ahead, one of these sublattices could be disordered, some of the lattices could be fully ordered, and these possibilities bring out a lot of interesting practical scenarios, which will, of course, some of these we will consider in coming lectures.
So one more question.
Yeah.
Can the all sub-lattices should have the same lattice parameter, or the lattice parameters should be different for all?
Okay, another good question. Should all the sub-lattices have the same lattice parameter, or can they have different? In typical descriptions of sub-lattices, you can see that the sub-lattice is no different from the main lattice except for its shift and its occupancy. So its symmetry is identical, its unit cell is identical, etc., etc. So the two sub-lattices are not distinguishable in terms of their shape of the unit cell and their symmetry. It is only they are distinguished by their occupancy and their origin of the sub-lattices. So typically that is the scenario we usually consider.
So in the previous case, you said that if the maroon one would have been similar to green, so can we have a situation like we tilt the axis at an angle tan inverse b by a, and we have a lattice at an angle so that we get a simple axis, and not getting in that rectangular central you said now. So instead of defining that rectangular central, we can invert the axis at an angle and take a simple plane along that direction.
Okay. Though I must confess that I didn't understand everything what you said, but if I understand your question correctly, you are asking me that instead of using my basis vectors as a and b, I could use my basis vectors as something going from here to here and from here to here, right? That's what I want to do.
Yeah.
All these other choice of basis vectors are possible and they are allowed, and perhaps in some scenarios you would do such kind of choice of basis vectors, especially if you are trying to study phase transformations and you want to compare two structures. However, in all these cases you should notice, as we had pointed out before, that your basis vector should start at a lattice point and end at another lattice point. That's very, very important. You could, for instance, choose the way I told you one basis vector. You could start from one lattice point here and choose the basis vector as one of these very far away. But nevertheless, the starting point and end point both should be lattice points, and you cannot choose, for instance, this is a disallowed case. I start from a green and go to a brown. So if I draw a basis vector which goes from here to here, this is not an allowed basis vector for this kind of a structure. So I have these two subcrystals, one with green circles and one with brown circles, and the supercrystal is a superimposition of these two subcrystals. So let us now break this lattice also into two parts. Like I can consider the original lattice, which is actually, to be more precise, a superposition of both the brown and green positions as a combination of a lattice which consists only of green positions and a lattice only of brown positions. Again, you should note, just to emphasize the obvious, that lattice positions are actually points. They are geometrical points. In other words, they can have no attributes like color, taste, color, or any one of those attributes. They are zero dimensional. But just for the sake of clarity, I have put certain kind of colors to them, and that should not confuse with any kind of motifs we are putting on those lattice points. So we can clearly see that this structure can be thought of as a superposition of two sublattices, but shifted with respect to each other. So what is the shift vector in this case? This being a two-dimensional lattice, you can see that the shift vector is a plus b by 2. So these two sublattices are shifted with respect to each other by half the diagonal of the original unit cell of the cube, which is a plus b by 2. So by considering these simple examples in one dimension and two dimension, we have explored the concept of a sublattice, and we will later on see that this concept of a sublattice and a superlattice is very, very important, especially when you try to define diffraction patterns from these kind of ordered crystals, which is what the question of Mr. Patel pertained to. Before we proceed further, especially to these three-dimensional lattices, let us take up some simple examples just so that we revise our concepts on what are lattices, how do we make crystals out of them, how do we define the lattice parameter, and what are the alternate choice of unit cells. So we will consider a few examples, few solved examples to understand these concepts. So this first example, example number 1, pertains to the decoration of a one-dimensional lattice with a two-dimensional object. So For instance, suppose I have an array of points in 1 dimensions, which is infinite in 1 dimension and which has got a lattice parameter a, and the question is that I want to place an motif or an object, to be more precise, in the shape of an arrow mark to create a crystal of lattice parameter 3a. So let me re-emphasize the question, the first question, that I want to place an object in the shape of an arrow mark. So far I am calling it an object or an entity, I am not calling it a motif, and it will become clear when I do the example that why I cannot call this, why I cannot do this if I call this a motif. Okay. So I have an arrow shaped object and I want to make a crystal of lattice parameter 3a. I would like to describe this crystal in terms of our familiar language of the lattice and the motif, and I would like to address the question that how the symmetry of this original 1-dimensional array is altered when I make this crystal. So it's a very simple kind of 1-dimensional example. I will see that there are 3 methods by which actually I can do the solution, and method number 1 is, as I pointed out very cleverly in the question, I only have a shape which has been prescribed to me. I have not prescribed a color, I have not prescribed a size, I have not prescribed an orientation to that kind of an object. So therefore that is the freedom which I have in my hand to choose, and that's what precisely I have done in the first example or the first method, wherein I take this array of points and I do not even use the word lattice so far, though it would qualify for a lattice if you independently considered it. So as we shall see, after the crystal has been made, all these points will not be lattice points. So let me take this array of points and I put a large length arrow mark on the first point, I put a slightly smaller arrow mark on the second point, and an even smaller arrow mark on the third point. Having done so, I will go back and pick my first arrow, make a copy of that arrow and put it in the next lattice point. I will make a copy of the arrow which is medium sized and put on the point next to it. I will pick my smallest arrow and put on the point next to it. I will do this process ad infinitum along the positive x direction and along the negative x direction to obtain a crystal. Now clearly this is not truly a 1-dimensional crystal because it's got a motif which is extending into, or an object which is extending into the 2nd dimension, but this is a nice illustrative example to understand the basic concepts. So let us try to use a familiar language of crystallography to understand the crystal we have just generated. Clearly the repeat distance of such a crystal is 3a. The original lattice or the original array of points had a repeat distance of a, but once I have made a crystal by putting these arrows, and I use the trick of actually changing the size of the arrows, only 3 sizes I required because I wanted to just to distinguish 3 types so that I can extend my lattice parameter to 3a as it has been done here. So I have a crystal which is now repeating itself every 3rd point. So first there is a big arrow, then there is a big arrow, then there is a big arrow. So now I have made a crystal of lattice parameter 3a, which is what I wanted to do. So clearly I have got a crystal of lattice parameter 3a, but now where are the lattice points? Obviously this is not a lattice point because you can see this is not the fundamental or the shortest lattice translation vector. The shortest lattice translation vector now goes from the first big arrow to the second big arrow, which is the repeat distance. So clearly the points in the middle, the 2 points in the middle, are not lattice points for the crystal I have created. So the lattice points would be the ones, for suppose this is a lattice point, then this would be a lattice point and this would be a lattice points. Of course I could have alternately chosen the origin of this lattice as the medium sized arrow, in which case only center or the bottoms of these middle shaped arrows would be lattice points, and as a third choice I could have done it as the smallest arrow's bottom also as a lattice point. But if I do that, then the only points which are lattice points will be the bottom shaped arrows, the points on which the bottom shaped arrow sits. An important point to note here is that there are infinite possibilities at my disposal to make this crystal even by this one method which I have considered, right? I could have made the shapes of the lengths of the arrows very different. I could have chosen this twice the height, I could have chosen this half the height, this is 1/10 the height, and I could just play this game indefinitely and I would get an infinite number of crystals which have a lattice parameter 3a. Only making sure of course that whatever I put here, I put the same thing here, whatever I put here, I put the same thing here, and so forth. So now the second question I would like to ask, I have known what's the lattice now, what is the motif? The motif now is not a single arrow, but a combination of 3 arrows as shown at the bottom right hand side of the figure, and this motif goes on to decorate the lattice. For this is a lattice point, I put 3 arrows, and what is the distance between the arrows? It's a very precisely fixed number, which is 1/3 of this 3a, which is a. So if this is a and this is a, then this is also a, while the repeat distance becomes 3a. Now, so this motif has to be put identically at each lattice point to generate this one-dimensional crystal. But I have not exhausted all possible ways of generating this or all possible types of ways of generating this one-dimensional crystal. So let us consider one more method in the next slide, wherein I have this original array of points spaced A, and what I do this time, I change the color of the arrows. I maintain them of the same height and same width, but what I do is that I put the first arrow, a green arrow in the first point, I put a red arrow in the second point, and put a blue arrow in the third point. Go back to the fourth point, put a green arrow, then put a green arrow here, put a green arrow here, and so forth. I'll put a red arrow in the second, then I'll put a second, the fifth point I'll put a red arrow, and so forth. I'll go infinite in the 2 dimensions. So by changing the color here, I have now created a crystal as shown in the bottom figure, which has a repeat distance of 3a. In other words, the lattice parameter of this crystal is 3a, while if I had originally considered this lattice at the top, it would have had a lattice parameter of a. But clearly, as I had pointed out before, the only lattice points we can consider are not every arrow, but every third arrow center or every third arrow bottom is a lattice point. And now, since I know what's a lattice, now what is the motif? Again, it's a combination of 3 arrows as before, but now there are 3 arrows of the same size but different colors, and this combination of a green arrow, a red arrow, and a blue arrow with the distance between them being a is my motif. Now if this motif goes on to decorate my lattice, which has a lattice parameter 3a, then I would get a crystal in 1 dimension, which is infinite.
So by considering different types of arrows, are we decreasing the symmetry of the crystal?
Very good question. Mr. Debstosh, a very important question, that by considering different type of arrows, are we lowering the symmetry or changing the symmetry of the crystal, which if I had to consider only one type of an arrow, I would be constructing? A very important question, and in fact that is the third question we are asking ourselves. How is the symmetry altered on the formation of the crystal in these cases? And we will answer it in a moment. So let us consider a method 3, wherein I don't play with the colors or the sizes, but I play with another degree of freedom which I have got in my hand, the orientation. So what I do, I take my original array of points and then make sure that I put, say for instance, one up oriented, then one more up oriented arrow at every third point. Then I can choose any other 2 orientations. I could have in fact chosen 2 up and 1 down, or 2 oriented like this. So like in the previous example here, I could play with various kind of colors and I would actually have an infinite set even in this subset. Similarly, by playing with orientations here, I can actually have an infinite set of ways merely based on the kind of orientations I can explore, and therefore I can make infinite number of crystals based on the orientation. So what I did here, I changed, only thing I make sure that the orientations of the second arrow and the third arrow are both not simultaneously identical to the up arrow. I could actually put a one up arrow, another up arrow, but a down arrow I have to put, then an up arrow, then down arrow. That would work fine, but I cannot put all 3 up arrows, in which case I would make a crystal of lattice parameter a. So as before, the crystal has lattice points located here, here, and here, and the point to be noted is that the motif now consists again of 3 arrows, one up and the other 2 oriented as shown in the figure. So I take this motif and put it at each lattice point, and then I would have a 1-dimensional crystal which is now having a motif in which the shape of the arrow has been just tilted with respect to each other and not altered in terms of its color or in terms of its size. So I have considered now that actually I can go ahead and make 3 infinity sets, not just 1 infinity set, but 3 infinity sets of crystals in 1 dimensions, merely given the fact that I have a constraint that the shape of the object has to be an arrow mark. Okay. So now to answer Mr. Deptosh's question, that what happens to the symmetry, okay, when I form this crystal? In some sense, I can talk about the symmetry of the crystal being lowered from A to 3A. So the original crystal had a translational symmetry, or the original lattice, if I look at this lattice, had a translational symmetry A, and the newer crystal has a translational symmetry of 3A. And that is reflected in the fact that every third lattice point is only a lattice point when the crystal is formed. Now can we analyze it a little further in terms of the other language we have learned so far, which is the language of the sub-lattices, and that would also answer the question which Mr. Ravi Prakash Srivastava asked, can I have more than one sub-lattice? Can I have more than 2, in fact his question was. And clearly there is an example right here sitting in front of you wherein we can have more than 2 sub-lattices. In fact we have 3 sub-lattices. In this example, for instance, I have one sub-lattice located at the origin 0 with all green arrows. So this would be that sub-lattice, and if I consider that crystal, it would be a sub-crystal with an green arrows. The second sub-lattice would have its origin shifted at a distance A from the original lattice, and it would be complete, that subcrystal will be completely populated only with red arrows, and the third subcrystal would be populated with blue arrows, but its origin would be shifted at distance 2A from the original lattice or the green lattice. Therefore, this is an example additionally to show you that the concept of sub-lattice can be applied to understand such kind of crystals which are ordered crystals.
Excuse me, sir.
Yeah.
In the examples you have shown different color arrows. Here we will count the color symmetry also.
Very good question. Mr. Ravi Prakash Srivastava is invoking an higher order concept, a concept of color symmetry. So far when we did the chapter on symmetry, we only considered normal symmetry. Color symmetry, if we invoke, then I can actually describe an operator which not only shifts my positions but also changes its color. In such a case, actually my lattice translation vector could become A, because now what I can define an operator, for instance, which would move a distance A and change the color from green to red. So this is my new specialized operator. It's a very more sophisticated operator than a mere translation operator, and in such kind of examples are actually very interesting to work with, and in fact you can have color symmetry groups and they come in very handy. These examples with arrow marks at present are merely what you might call geometrical constructs, and the practical examples of such kind of color symmetry would be wherein we have an interface, and on one side of the interface, for instance, you have an atom which is of one kind. On the other side of the interface there is an atom of a different kind, but then there is a mirror plane which can take an atom of one kind to an atom of the other kind across the interface, and such a symmetry, clearly there is a mirror symmetry, but the mirror is not a normal mirror, it's a color mirror, because it's changing an atom of one type, say a black atom, to a white atom. Now you could have a generalized operator wherein you're not just dealing with 2 colors but n colors, and those n colors, in other words, suppose, let me go to the board and explain you this concept. Suppose I had a square. So a normal symmetry operator at the center would be a normal 4-fold operator, which I have drawn here. Suppose now, which means that basically you have the 4 corners. Suppose I put circles in the 4 corners, they are all white circles. Now suppose instead of having white circles, I use different colored circles at each corner. To start with, I will use circles of 2 colors. So I have a blue circle and a white circle. So what is the rotation operator in this case? So this is obviously not the normal 4-fold, so let me cross the normal 4-fold off. In this case we have color symmetry. What it does, the rotation operator can take a blue circle, rotate it 90 degrees, but turn it into a white circle and put it here. Further, it will rotate it by 90 degrees and put a blue circle here, so it will invert the color, change the color. Then it will rotate by 90 degrees, put a white circle, then rotate 90 degrees, put a blue circle. So this object, if I do not consider color symmetry, what is the kind of symmetry I have got at the center? The kind of color symmetry I have got at the center is nothing but a 2-fold. So if in the absence of color symmetry, suppose this whole recording was going on as if all these colors are identical, then I would have a two-fold symmetry merely here. But in the presence of color symmetry, I can think of as an operator, a slightly higher sophisticated operator, wherein this is now a color fourfold, which not only rotates but changes the color of the object. As an extension of this concept, I can go ahead and put more colors. So let me put more colors. So I can put a blue in the first one, I can put a red in the second one, I can put a yellow in the third one, and I will leave the fourth one as an empty circle. So what kind of a symmetry operator I have got here? I have got a color symmetry operator which has 4 operations which it can perform. It can rotate first by 90 degrees, leave a red, then it can rotate 90 degrees, leave a yellow, then it can rotate and leave a white, and then the 4th time it rotates, it will leave a blue. In other words, there are higher order symmetry operators which are possible, which can do things which are more sophisticated than the normal symmetry operators which we normally deal with in normal crystallography. And there are cases, for instance, when I want to describe, for instance, magnetic systems, wherein not only I have an atomic position, but I also have a magnetization vector. So I want to describe a system wherein I am describing a combination of properties, just not the atomic position but also the magnetization vector, and in such cases you may find that these additional symmetry concepts come in very handy in describing these systems. To answer this specific question, I have a green arrow here. I could describe a symmetry operator which takes in the first stage it to a red arrow, then in the second stage you take it to a blue arrow, then bring it back in the third stage to a green arrow. In such a case, it would definitely be a lattice translation vector of A, but then the operator itself is taking care of the fact that I have a motif which is of 3 different colors. So these are more sophisticated and more difficult ways of describing the same crystal. This being in sort of an elementary course, we will stick to the normal concept of a normal lattice, and we will stick to the normal rotation and the normal translation operators which can do my job. Now let us consider another example to understand our familiar language of crystallography and the familiar concepts of lattice and a motif. And this is the example of a graphene sheet. So I have shown here a part of the infinite graphene 2-dimensional layer, and you can clearly see that in a graphene sheet you have carbon atoms which go on to sit at various vertices of this hexagon. So you have a graphene sheet which is here, and you all know this graphene sheet is sp2 hybridized, and it is ideally speaking, in a more mathematical way, it's actually 2-dimensional. If you stack these kind of graphene sheets one on top of the other, then you will go on to obtain a graphite structure, which we shall consider later in one of the lectures. The questions we are asking ourselves here: does the array of points at the centers of the carbon atoms, that means the centers of these carbon atoms, are they all going on to form a lattice? We will then try to describe this in terms of the lattice and motif concept, and we will also try to identify the unit cell. So let us try to answer the first question. Do all these centers, for instance I take the center of this sphere, center of this sphere, center of this sphere, do all these centers of all these spheres, which are basically carbon atoms, which are sp2 hybridized, form a lattice? The answer is no. Let us see why the answer is no. So if I take an atom, for instance sitting here, I can clearly see there is an atom to its right at a distance. For instance, suppose this is my carbon-carbon bond distance and I call it A. Clearly there is an atom to its right at a distance A. Now suppose I consider an atom B, then I clearly see there is no atom sitting to its right. So the environment of point A is different from the environment of point B. And what is the requirement of a lattice? That every point should have identical surrounding. So clearly, as the surrounding of point A is different from the surrounding of point B, both of these A and B both together cannot be belonging to the same lattice. So now what is the lattice and how do we describe it in terms of a unit cell, a motif, etc. is the next question. So I will just merely for my convenience color all those points which have identical surroundings, the carbon atom sitting on those lattice points. For instance, the 2 colors I shall use, green and grey, and the green ones are the ones which are, for instance, forming let me see which one I have used. So I am using the gray atoms to be sitting on the lattice points, and the green atoms will not be sitting on the lattice points but will be part of the motif. So now, what is the unit cell? The unit cell, as you know in the conventional representation, has lattice points at the corner. In 2 dimensions it has to be a parallelogram, in 3 dimensions it has to be a parallelepiped, and we should have lattice points at the corners or at the vertices of such a unit cell. So my unit cell would be this blue colored rhombus, and my lattice points are the corners, the gray colored spheres of carbon, and my motif now consists of 2 atoms of carbon, the gray atom and the green atom. Of course, in terms of its chemistry, these 2 carbon atoms are exactly identical, but in terms of our understanding, it's now a 2 atom motif, a 2 carbon atom motif, one of them sitting at the origin of this cell, the other one sitting in a position which is displaced with respect to it. Now for clarity, let me draw this unit cell separately. So this is my unit cell. Let me go down to the next picture, wherein I have these full carbon entities shown. So I have my unit cell, I have my motif which is now decorating this lattice which is in the shape of this rhombus, and this is now the 120-degree rhombus. As you can clearly see, the cell, the supercell, which I can form by the combination of 3 such blue cells, of course one rotated with respect to other, is this dotted line showing this hexagon. So this is my unit cell, and this is therefore has got hexagonal symmetry, and therefore the lattice is hexagonal lattice in 2 dimensions. So the motif is now this green and this gray, which form the structure which can be repeated. We had pointed out that this is truly not the unit cell, because if I try to repeat this unit cell, then there will be an overlap of the atoms from neighboring unit cells, and therefore the true unit cell is actually obtained by cutting off the parts of the atoms which are not present within this blue area, and this is the picture which is shown now at the bottom, and total contribution to this unit cell will be 1 from these 4 atoms. Put together, these 4 atoms sitting in the vertices will give contribution of 1, and this green one will be an additional carbon atom. Therefore there will be 2 carbon atoms within this unit cell, but the number of lattice points per cell still remains 1, and therefore this is a primitive unit cell of the graphite structure.